Welcome back, guys. Okay, so this week we left off with some debugging last week. We did a lot of stuff, and we have fixed setup. I guess we just fixed the entire setup to make it work in general. Also, I remember writing to do. So this week we are supposed to fix why the process is not switching after the time slice is over, and then we are also supposed to check why the page table entry for GIC is not working. So there are two to-dos, but in general I'll just give you an overview. It's just that we are writing our own kernel, and so far we have our start. This will be the initial entry point for anything, because in general if you have a QEMU that is emulating the CPU, and whenever it gets a run loop after the bootloader, the first thing that it looks for is the start. So this is where everything starts, at least after bootloader. And here we have initialized the vector table, and we have some X stuff, but that doesn't matter. But finally we jump into kmain, and if you want to know about the steps that we have done, you can just look into our previous videos. And in the kmain we have the actual UART message that's gonna say that the kernel has started. And then we have some timer initializations, because we are gonna drive our kernel based on timer interrupts. And we also have the kmalloc implementation that's gonna internally use a bitmap array to keep track of the physical memory, and it works perfectly fine. And yeah, we had a lot of to-dos. Right now we have the final thing, that is check wire. Right now there's one thing that I haven't explained last week, was that what exactly is the setup for the user programs here. So we have initialized two processes, and we have set the process 1 as the current process in the scheduler, and we are jumping into the first task. That's all we do. So as soon as we get into the first task is supposed to run for a certain time slice. Once the time slice is over, the scheduler, where's our scheduler? Yep. Once the time slice is over, our scheduler will be in this points here, and it will check if it's still running and the time slice is 0. It will just reset all its options and push it back to the queue, because here we set it to the current, and now it will set the current to back of the queue, and it will pop the queue. That would be the second process. So we have two processes, so it's going to be scheduled like this. If A was scheduled first, the second one will be B, and the third one will be A, and the fourth one will be B. But every time we reach this scheduler, the actual code that is running is the scheduler's code. And when does that actually happen? Whenever there is a timer interrupt. Whenever there is a timer interrupt, our scheduler code will be running, and it's going to check if the current process has enough time slice. And how often does this timer interrupt fires? That's what we have defined here, and it's going to be 1 milliseconds. Yep, it's going to be 1 milliseconds, and 1 millisecond is a really long time. I was talking about it for a long time in the previous stream. Yeah, I guess that's all. Now that we have a good overview of what we are trying to do, because I was getting some comments about people not having any context of what's going on when I start the stream. So I believe maybe I guess it's fine to get a little context over what's happening here. Okay, now that we have the actual to process scheduled, now let's just run it and see what the fuck is happening. Okay, I don't have a okay. Okay, it's okay. Okay. What? I fucking forgot my hotkey. Okay, let's see. Yeah, I use Windows and Linux quite often, so Windows, Linux and Macs quite often, so it's just that the hotkeys that I have to try out over that is completely different. My muscle memory just gets a hit whenever it tries to do it. What am I gonna do? This is just self-promotion, I suppose. And we can switch back to our thing, and also maybe we can move this. We can have another desktop here. Move this here. And have it full screen. Okay. Now it should be good. Simple kernel, simple MU. And let's build it. Bash. Okay. And let's run it. Okay, so things are running. For some reason, things are running. We have initialized stuff. Oh, you don't have that much RAM. I remember that. Wait, I wrote that somewhere. What was that? How do we find that? I guess it must be in my MMU, because I remember writing that if condition somewhere. You don't. It's here. Okay, it's inside map page table entries. Oh, okay. If we try to map more than one entry, okay. I just remembered that. Yeah, there is a flaw in this code, as if there's two entries. What is that? Because my page table is just 496 bytes. That's 1 KB, 4 KB page table. So in case I allocate, let's say, 16 MB of 16 KB of bytes, It's in case I say kmalloc and 16,000 bytes, then I need 4 page tables. So in that case, I need to come into this function and I have to allocate 4 page table entries. But for some reason during that testing, I found out a bug, and that was not allowing me to do multiple mappings, but one mapping was just working fine. So that's why I added this print message, and now it's gonna fuck us. That's just sad. Okay, so let's see why it will. I don't remember exactly what to do. Create a separate L2 table for every index. What does that mean? Why do we need a L2 index? L2 index is L2. L2 means it would be within L1. So within L1, what would be the address within L1? Do we have that somewhere? L1. I don't remember the name. What the fuck is this name? I suppose it's just no, I'm just trying to figure out to find out the by bits for every level, because within the page table we have multiple levels and every level can hold different ranges of memory. And so for L2, what's the range? I don't remember it, but that's what I want to look. And it should be page table levels. Let's try this. Do we have the documentation? I think we have it here. Okay, this is the one. We can have it 4 KB. Yes. So in level 1 we have like 512 GB and every index will be 1 GB. So that's fine, because my entire RAM is just 2 GB, so I don't have to worry about L1. But my L2 is just my L2 table is just 2 MB. So in case here I have it like if the I is index is 0, then I just use L2 base. If not, I'm using L2 0 physical. What does that mean? I guess this is like a hard-coded way of doing it for just 2 indices, because let's say if the index is 0, I'm using L2 table as this range, this address. If it is not, I'm using it as this address. But I might have to add this dynamically, because I can have as many as here. So first of all, I need a memory location where I can dynamically increase this. And one more thing is that within this table we are gonna have how many entries? 512 entries. So that is how many indices is 512 entries? I think it's the same like here. Where is it? Yeah, it's like this. So if it's that, then I need a location where I can just simply keep growing the table entries. No, just the tables, because I need a location, because here my L0 table is located in this location, L1 table is located in this, L2 is here, and for and I have two more L2 tables. Have I used this anywhere? How do we search it? I think it's control. Oh shit. Did I just close that? Oh fuck. Fork. It's here, okay. Oh, let's see. It's here. We're simply just clearing it. We're not using it anywhere. Actually, we are not supposed to hardcode things like this. I think this is what we used as the second indices output, but in general I don't think we need and also every index needs 1000 I would say in hex it would be 1000x, because 1000x is 512 entries, I guess. Okay, so in that case, do I have enough space here? Because I need up to what? I'm a bit confused now. What is that? I'm trying to write into. If it's 1 GB L2, then I don't think I would need anything. That's why I guess I just hard-coded only two things. Because there's only two possible, because I only have 2 GB of RAM. I mean, yeah, it can have, but I don't think I'm gonna allocate that big of anything here. I think my code should work already. It's just not gonna work if the entries are more than 2 GB, because at level 2 the size is 1 GB, so one entry can hold up to 1 GB of RAM. So I should never be able to, I mean, at least in my case, I should never be able to shouldn't be able to allocate more than 2 indices. There's enough space there. Okay, let's see what was that number. come here, we tried total allocated. Wait a minute. I don't know. I'm just trying to see. We want to figure out this point of time, and where do we stop before that? Maybe that's why I need to write a little bit of better comments or better print messages right now. They all seem nonsense. Okay, let's jump into my K-main and just do the manual stuff. Okay, we are here. Allocating. Okay. And what is res? I believe that might be within Kernel, so let's leave that. And the pointer, do we have a pointer? The pointer is here, so that means we did not allocate. Okay, so we are supposed to debug it within Kernel. And first of all, what did I try to allocate? I tried to allocate 1600. And what's wrong with that? It should be just fine. Where's this current index? Let's get into Kernel. Here we have the res. Okay, leave that. And we are trying to total allocated is 4. That's fine. And we give the current index. Total allocated is 4. It's 4 here. And then we take the first index and we convert it into physical base, and we map the table entry for VA, and the current index is 0, and we get into map table entry with PA, VA and total allocated. What is total allocated? What is total allocated? Total allocated. Total allocated is the one that's fucking us. So we are supposed to figure out where do we add that value. Oh my god. Where is it? Total allocated. How do we find it? Okay, we have it here. Total allocated is just 4, and 4 is the actual thing. It has to have 4 because we're trying to allocate 16,000 bytes. That means there's 4 pages. Then it's correct. It's if the size is less than 4, we set 1. If not, we do some magic and we set those bits and we return that 4. It is perfectly fine. And one more thing is that, well, okay, it's just fine. Maybe I just have to remove that if condition. But I have a doubt, and I need 4 page table entries. 4 KB page table entries. That is this. But I am not even going into this third level. I always set 2 as the block entry, so every one there's only 2 possible values. I just set 1 GB of memory as block, so everything within that 1 GB will be valid. So I don't even have to worry about the third thing. So as long as I get into, so I think this is what maybe if I have to then maybe I have to set everything within a fourth. I mean, inside the third level, then it would be easier because I can just go 3 times within that, because as many as times this total is, then I can loop over that and set the 4 KB pages. But because right now I can only set 2. And 2 covers everything, literally everything. Wait, what the fuck am I doing here? So physical pages start from 8,000. Yeah. I guess there's another issue here. Okay, well, let me just start by thinking what I have to do. Okay, let's start some to-do here. Let's start some to-do here. Two. Okay. What exactly do I have to do? I need. What do I need? I need. I'm setting block entries in level 2. If I set block entries in this level with just 2 indices, I can cover 2 GB of memory. Currently, I'm setting block entry in level 2. So 1 index would be 1 GB valid block. So, there's only two possible indices. This is fine, but what if I want granular approach? Because I don't want to just simply set the entire block as valid. That that's just not that's just not good. I mean, it's going to it's just not good. I guess it's that simple. It's just not good. Maybe we'll have to allocate things within level 3. Okay, let's see. What do we do? We have the total value that's going to be the divisor of the car total divided by 4 kb. So it definitely perfectly aligns with applying the level 3 entries. But in case if we just want to do level 2, what would be the case? We have to have a we have to multiply the total into 4096 and then compare it with if it is less than a certain address, then we can tell that either whether it is within index 1 or index 2, and then decide if we want to add the index 2 or if we just want to add index 1. So there's another issue. What exactly am I doing here? I have the L1 entry and I'm trying to create a table descriptor for L2 and I set that. Okay, that's fine. And then I go into L2. Inside that I create a block entry for the index, and it's always going to be 0 or 1 because we are only going to try to allocate 2 GB of memory. So in that case, every time I'm getting into this function, I don't even have to try to allocate anything, because probably even the first time when I call this function, at least one index is going to be allocated, and for most parts probably one index is going to be enough. So what is the point of getting into this function? Why not just whenever this called once, I just allocate it and just return true somewhere here. Or I'll have to implement the level 3 entry. That way every time I get into this function and doing this for loop has some value and it actually does some work. Mm, I think I'm just gonna implement the level 3 entry. In that case, I have to also calculate the current index within L2 table. Index within L2 table, and then I have to just make the block descriptor. Okay, I'm also trying to do identity mapping, VA to PA. What do I do? Which version should I implement? Let me just write down all the options. So this is not to do, this is just current version. Currently, this is just currently. To do, either I have to implement level 3 entry, L3 entries of as I have the total pages. They are needed. In that case, I get a valid virtual address. I find that within L1, and then I find that within L2, and then I find that within L3, and I set the table. I think I can do that. It shouldn't be that hard. I just have to find this value. Okay, calculate L3 index. Because what does this do is that, so if you have an address, as you can see, the address, every address is separated into several bits, and that bits are used as the index. So if I have to calculate L2 index, then what I do is that I shift till 21, because the 21th address is the one that is used here. So in my case, now I have to implement L3, so I have to shift till 12. Okay, shift till 12, and this still stays the same because we have 9 bits that are inside this. I guess it's 9. It's 20. No, I guess it's 9. No, it's 11. Yeah, I think it's 11 bits. So it still stays the same. We just take the final bits. Okay, that part is done. I think we have the table descriptor and block descriptor, but in this final there's only page descriptor. Now we have to figure out how we can, because currently I was only working till page 2. So in level 1 I set it as a table, because level 1 points to a table, and within that table, which is the level 2, we set a block entry. But now we still go, so within level 2 we are again going to set a table entry, which is going to be the third table. Within the third table we are just going to set a page. So we probably don't need block entries. We will need what's that, page entry. Let's see, inline 64, make page entry 64, physics, and what it's going to take. Yeah, it's going to take the actual physical base. Yeah. Okay, so now we have to do the final thing, that is to figure out how we can set that entry. How do we set a page table entry? Because for a table entry we set description as valid and description table, that is, I guess it's 0 and 1. For block descriptor it's 0 and 1 and 0. Yeah. I think for table entry it must be 1 1, I guess. Do I have that image? Let me go into my setting, enable unit, table layout. Probably this is where it's not here. Debugging access denied. Maybe I'm getting ahead of it. I think I'm getting ahead of it. This is the one. As you can see, if it's a table descriptor, we set it to 1 1. If it's a block descriptor, we set it to 0 1. And if it's a page descriptor, we set it to 1 1. How does that work? Wait, in my page table, in my page descriptor, I setting this to 1. One to the first bit and 0 to the so it's 1 0 0 1 1 1. Why is it saying that here? That's wrong. It's not supposed to be like this. Wait, I had some other. Uh, nope. Now I'm a bit confused because from as per this, the table descriptor should be 1 1. But I'm setting it. I'm setting 1 to 0th position and 1 to first position. Okay, I am setting 1 1. Fine. It looks like I didn't read it properly. It looks like 0. I'm just shifting 1 0 times. I don't know why I did that. And here I'm shifting 1 time, so it will go into the first bit. So it is 1 1. And then we have the block descriptor. Block. Okay, so anything that we set in the level 3, if it's 1 1, it's just going to be a page entry, even because in level 3 there is no table descriptor. I guess that's why they kept it as 1 1. Okay. Makes sense. In that case, do I need anything special? It still starts from here, so I think I don't need anything special. Let's just copy this and paste it here. But there's one issue. I think we'll have to do something with this value. I'm doing that operation to shift everything to the 47th bit, I guess. I think it's fine. It's just fine. there's another issue. Because my main MMU, when I initialize things, I set L2 entry as a block. If I'm setting L2 entry as a block, then it in this L2 there's already there's already an entry for 1 GB of memory. That's just sad. I think we'll have to rip this off and convert this into L3 entry and then convert that into L3 entry. Only then it will work. Because here if I have a L2 entry, or maybe I can change the entire table where I'm looking into. Then that would mean I have two different locations. That's not good. Okay, so let's write it down because we might need it someday. Remove the block descriptor L2 and move it to L3 page entries. Okay. So at least at this point we have a hard limit on what we can achieve, and I think because there's 1 GB of memory, I mean 1 GB block that is already assigned, and my actual physical page starts from what, 8,000. Physical page starts from 8,000. So I think as long as the entry is not greater than 512, I think it's good. Let's just put 200 then. No, let's just put 20, just in case if we fucked it up somewhere, we can get this error message again. Okay, now the second issue is that we are trying to allocate something again and again every time, and that's not needed because there's only 2 entries and that's already most probably allocated. So let's just allocate this once and get on with it. How can we do that? Let's just create a global variable, static event 64. I think I don't even have to allocate it again, because even for the first entry that is already there, what am I even going to do within this map? Because as I said, now my range starts from 8000 and I have a 1 GB entry there already. And so if I'm getting into here, what's the point? There's literally no point in coming here. There's an entry there. Wait, let me double check that. Now I'm having bit convolutions. So we have the first table. There's L1. Wait, am I allocating till L3? Oh, is it really? No. L2 entry is already there, so L0 entry is not needed, so we don't do anything. And we have the L1 entry and we calculate the index, and it's just going to be 0th index because it's 512 GB. And we make table descriptor for that. And then we calculate L1 index. L1 index is just 0. We set a table descriptor for that, and we get into L2, and L2 entries are going to start from our 1 GB entries. So it's like VA 0x0000 will be mapped to 0x800 something. So in case if I need okay, I think we still have to do this mapping. Or do we, let's say this is how the address looks, 1234 123 and let's say this is what we want to access, and then we get into L1 table. That would be just 0th index. In L2 table we are still no in L2 even in L2 we are still in the first index, that is the 0th index, but we have entry for I guess the second index, that would be starting from 8000. So I think we need to add this but we are not supposed to overwrite any existing entry. And how do we do that? How do we do that? Let's sell to physical base. I don't know. I'm missing something. We have an entry. I think we have one entry. That is all, because that's hard coded. Because whenever I get into my MMU unit, I create one entry from this to this, and it's going to be a 1 GB entry. And everything else I add within L2, because within L2 I have two index, because L1 it's just going to be the same thing, but in L2 I have two things. One is from the initial one, that is 802 to 80, and second is the actual, this is for virtual and this is physical, but then we also have the entry from, what is that, from the what is this, I don't remember what is this. Yeah, this is for the UART. And then I have an entry for these two stuff I just added recently for the GAC and GACD, which is not working. So let's remove these two entries. Okay, so my map is just going to work with L2. It does not have to care about even L1. In L2 base, I just have to add more entries if needed. So let's see. In that case, I don't need L1 entry, I don't need L2 entry, I don't need L1 entry, because L1 entry is going to be the same thing and it's already there. Now I need L2 entries. It's possible that I might need L2 entries. And L2 entry, I just create the index. I find the index for that. I make a block descriptor. I set the table entry. I'm also adding a physical to physical mapping. Why is that? I think this is not needed. Let's just add virtual to physical first. And I'm adding it into current L2, which is, if it's I0, then it will be stored in L2 base. If not, if it will be stored in L202 base. I think this is not needed because I think there's only one L2 table, that is L2 base physical. Within L2, because this is already stored and it has 512 indices. Within that indices, we just try to find the current VA and we set that index to a block. I'm just wondering if there is any way to confirm that this block hasn't been used before. I mean, that's the whole point of keeping track of it, but we do have some memory that was used before MMU, before even initializing this bitmap array, but I think they don't collide. Let's try. Okay, so things are fine now. We are able to index it and we are able to print it too. Let's see if our main, if we go into our kmain and we use kmalloc to allocate some bytes and we have printed it, so the memory is working. And then we allocate 2 tasks and we enable the interrupts and we start it and we jump into the first task. What is our task? Our task is just simply 2 while loops, but it needs to be interrupted by the scheduler. Okay, I guess now we can, hopefully if things are going well, we can move on to the next debugging. But in case we get a false sense of things are working, then we might be looking into wrong errors. I guess I have to take that gamble. But my only reassurance is that we try to allocate and we are able to get the things printed. That means allocation is working, and in general it should work because there's only one page table entry and that table entry is already allocated and it's a block descriptor that's just saying that this entire 1 GB is filled. So no matter what I do, that page table is there, that memory already exists. Now let's just debug the scheduling part. Push user process 1 to head. We have initiated 2 tasks. Let's just say art printf initiated 2 tasks. Okay, I have initiated 2 tasks, and then I have pushed 2 tasks, and I'm setting current this here, and then I'll start, and I think I'll never reach this, so there's no point here. Task 1 scheduled. Jumping into task 1. Okay. Now let's see. Where are we fucking? Let's see. So we have jumped into task 1. I think we have jumped into task 1. Right now I think maybe we just have to fix the timer interrupt. Let's just see if we can, if the task 1 is running or not. Running. I think it should run without any issues. No, task 1 is not running. Okay, what else can happen? Let's see. And first user enter, and I'm giving a context. I think it should be inside vector. I move 0 to SP, and I restore unearred. That's all I do. Maybe something with this. Disassemble first, and let's see. 1, 2, 3, 4. Okay, now we are inside the correct function. Now let's see what's in x0. Info registers x0. We have this, and let's see. Let's see, 10. It's just empty. Maybe our fucked up. We fucked up the context initialization. Let's see. We came a lock and we got I guess we have to add more print statements here. But the schedule did get enqueued, so I don't know. Let's see. Okay, stack. Use stack. We are taking the k-top as the stack, as the context address. Let's also print that context. Okay. Is there anything else we might need to print? I don't think so. Now I have a question. In case we got an index here and we set that to a PA, are we updating it every time? I think this is problematic. We have a L2 index. What would be this L2 index? Let's just see that. L2 index has always been 0. And every time I'm setting a different physical address. I think that's the fucking problem. For every time the 0th index, I'm marking it as a block descriptor starting from physical address somewhere else. How the fuck will it work then? What is it? Yeah. That's why we should not write stupid fucking code. See, I'm trying to at some point the final this 0th index will start from this point, and the ones on the top will be holding an address that does not exist. Yes. So all we have to do is that we just remove this. Everyone already has a 1 GB memory, so I think I can just hard code this in the MMU init. Or I add it once and this is not real good code because this is like a really bad thing. Global variable modification. But I just need to check things, so yeah. Why do I get print L0 index 4 times. And the current VA is still okay. I'm not printing the current VA. Mm-hmm. 0. Or maybe we also have to keep track of all the indexes that I'm using here. And what's the point of bitmap array? Bitmap arrays told me that these indices are not used. That's why I'm here. But bitmap array is keeping track of 4 KB. We set 0th index to that. Now we have VA. We have allocated a lot of stuff. Okay. Okay. And what is an X0? It's just fucking zeros. What I have to do is I have to break at this point and see this context, build initial context. I need to break at this, and I need to break it. Oh fuck. Okay, now if we run, so we are in the build context, and the build context is supposed to take the first argument as ctx. Okay, let's see, so or cdx, it's supposed to be x0, I guess. Let's see, x0. Okay, this is exactly what and even here it's all zeros. Maybe we'll just try 100 minus 0x. It's all just zeros. So even here at this point, okay, that is true, because at this point is supposed to be zeros. This build context is supposed to update things, I guess. Yeah. Okay, that's good, then let's just get into this then. Why is this build context jumping somewhere? Is it getting back to where it started? Context is supposed to have 30 registers. That is 4. And then it's supposed to have the return address. Maybe it does have it. Okay, let's try. If we jump here, we are back into that actual instruction. No, we are again back into build context. Okay, let's see what's in this. Okay, that's fine. That's not that is also not overwriting it. Now if we continue, we are in the main thing. Now if we check the same thing. Okay, we do have it. So it is partially at least working. I don't know how this changed, because it looked a little bit different last time. Now our x1 value, info registers x1. This is our return address. What is this exactly? Disassemble user process 1, and it is correct. The return address is correct. Okay, let's move on then. We're just moving all the registers. And finally we are going to do erets. Let's check the info registers. ELR. It's ELR EL1. But what? Yeah, the address is correct. But now if I I'm getting an what's that? Translation. Okay. We got a fault. Okay, let's check this fault. Now if we cat what's that? QEMU1 grep tail -n. This is the worst way to do tail, because it has to catch the entire thing and tail it. We are not able to access this memory. There's no entry for this. What we can do is instead of shitting this part, let's just not fuck it up. And if we don't fuck it up there, and if we run it and we still get the same error, and there's no access errors because in general there's only one index and it's already have been allocated. Now if you check the last, okay, we are not able to cat it fully. Okay, let's cat it now. The cat is taking forever. Okay, I have to open it in VS Code. There's no other way. And VS Code is gonna hang. But it's fine. We can at least will get some information. We it's just happening. The same thing is happening again and again and again. So the question here is, how the fuck did that location become unmapped? Because that's just a normal location and it's supposed to be mapped, because it was working. I mean, that part of code has been working just fine, but there's no fault here. That's what I'm wondering. Maybe we are not we are assuming something that's not there. We have all the errors enabled, and we are inside Kimu. And it's just repeating the same thing again and again. If I scroll with this, it's going to fuck me up. I guess. Okay. Okay. This is where it all starts. Let's just copy this then. Copy it. Did it yank? I hope it yanked. Now it's GPD done. Oh, fuck. No, it's not yanking. Now let's see if it's copying. Okay, what's going on here? I can close this or my entire computer will hang. Okay, something is executing, and I think it's my fucked up vector table. That is what it is. Where is it? My vector table, because my vector table has lots of b dots, which is not good, I know. And it's here. Yep, I have a lot of b dots. I have IRQ dispatcher, I have syscall dispatcher, I have default dispatcher, and I have not a syscall. But how did I even reach that? I'm not even supposed to reach that. Well, let's just put it everywhere. Okay, now what's the error? It's the same thing. Okay, that's not good. Okay, I guess this is going to be a different debugging session, because it's just going to take a lot of time. So I'll just continue this in the next session, guys. But the issues that let's just write the to do. Where's the to do? To do. We are jumping into some sort of loop. What is going on there? Okay, we'll see that. Have a good time. Bye.